In this lesson, we're going to learn how to solve equations using quadratic techniques, and we're just going to kind of touch on that today. We're going to use some stuff we already know and then add a few more things. And then when we do this lesson again, the next day, we're going to add even more stuff to it. So it kind of will take a few days to get through all of this. In this problem, I have x to the fourth as my leading coefficient. So my leading coefficient is 1 and my degree is 4. To factor this, our number one rule for factoring is always taking out the greatest common factor. So hopefully you see that we could divide by x squared here. I'm going to divide everything by x squared. And then what's left in my parentheses I'm going to try to factor. So I'm going to make my two parentheses. Factors of x squared are x and x. Factors of 12 when added together make 7. Hopefully we see that that's 3 and 4. So now this is me fully factoring this side of my equation. In order for me to solve, I set each factor equal to 0. So x squared equals 0, x plus 3 equals 0, x plus 4 equals 0. So now I'm going to find my solutions. This is where my graph crosses the x-axis. So I would minus 4 from both sides. X equals negative 4. There's one answer. How many answers am I supposed to have? Well, look at this. My degree is 4, so I should have 4 answers. So now I'll keep working. Minus 3 from both sides. X equals negative 3, so there's another answer. And then over here, to get x by itself, I really would square root both sides, wouldn't I? And since the square root of 0 can't be a plus or minus, I just have the square root of 0 here. Now the problem with this is that I only have 3 answers, and I know because I have a degree of 4, I should get 4 answers. So what happens is 2 of my answers are right here with this x squared. So this ends up being what we call a double root. And we've done those before, but now I want to show you what this actually looks like on the graph. So think about this problem. It's a fourth equation, right? Degree of 4. And so my graph crosses the x-axis at 0 twice, maybe? And at negative 3 and negative 4. So I graphed this on my calculator. Well, I actually used a better graph so you could see it better. But here's where my graph crosses the x-axis. Take a look at that. Here's negative 3. Here's negative 4. But the really interesting part is, instead of this graph continuing through 0 like most of them do, what did it do? It hit the 0 and bounced back up. That's what a double root looks like on a graph. It doesn't go all the way through. If it was coming up, it would bounce back down, or if it's coming down, it'll bounce back up. So just so you know, that's what that looks like on a graph. So you could actually pick out some double roots. And it kind of makes sense if you think back when we did parabolas. Look at just this portion of the graph right here. Whenever we got a double root, do you remember what happened with that? That was always our vertex, wasn't it? So it kind of goes along with parabolas a little bit when we're looking at this, is that we have that, this would be a relative minimum, right, is happening at that double root. And that would always be true. Even though we wouldn't call that a vertex in this exact problem because it's not a parabola, you can kind of think of it that way and see that that's happening just the same as it did with vertexes. So now number 2, same idea. I have a degree 5 equation now. So this is a quintic equation. The last one we did is actually called a quartic if you want to be specific, but polynomial is good for you guys. So I'm going to take out my greatest common factor, which in this case is x cubed. So when I divide everything by x cubed, I then have over a trinomial that I can actually factor. So we'll go x and x. Factors of 24 when added together make 11. You guys could do that as 8 and 3. So now, I should have 5 answers, right? So I'm going to set each of my factors equal to 0 and solve. So here I get x to be negative 3. Here I get x to be negative 8. And here, I actually have to cube root this, right? And I get x to be 0. But because there's a 3 here, instead of a double root, what do you think that's called? A triple root. So now think about what this will look like as a graph. If a double root bounced down and back up, what's going to happen with this triple root? Well, let's take a look. So I come down. I knew I had an answer at negative 3. And I actually had to zoom in on my graph, so you can look up here. I also have an answer of negative 8. So hopefully you trust me that when this goes to negative 8, it's going to go through there. I just really wanted to zoom in on this because this part right here is really important to see. This is the one I have in the poster in my room that looks like this. see how it almost like looks like the graph is hanging out at 0 and there's like this straight line right here almost? It looks like the graph is just stuck there and it's hanging out. That's where the triple root comes in. It's going to have that almost horizontal look. Like this is the ones when we were first learning domain that we weren't sure if they were a function. We were confused by that. That's this kind of graph right here. So when you see it kind of hanging out there, that's the example of a triple root. So it's like it bounced up, down, and back up again. And it just had to hang out at that 0 spot. And this is all occurring at 0. So that's really different because we're not used to seeing it kind of have that horizontal look at that exact point. I don't know if you guys are as excited about this as I am, but I think it's kind of cool. So we'll keep going with these. Go through all our different kinds of factoring here. This is a binomial, so I'm thinking maybe some difference of squares, dots, difference of two squares, but I do have a GCF, so I'm going to take out my x cubed here. I'd have x squared minus 196. So because it's two terms, I'm wondering, are they both perfect squares? And hopefully you're realizing, yep, x squared is a perfect square, and so is 196. So it's x plus 14, x minus 14. So now I have x cubed equals 0, x plus 14 equals 0, x minus 14 equals 0. So we get x to be 0 as a triple root again, because we had 3 roots there. And then we're going to get negative 14 here, right? And positive 14. And because we like to be fancy, we're going to probably write that as plus or minus 14. You don't have to, but that's a more concise way to write it. So if you want to do it like that. And again, let's take a look at this graph. I don't have the negative 14 on here because I wanted to zoom in again and let you see how that has that little horizontal look almost when it hangs out at that 0 point. So you can see what that triple root looks like. The next one then, here we have 5. So I have 2 terms again, so I'm thinking difference of squares. I can take out a y, just a y. So I have y to the 4th minus 144. Now remember, we're looking for the difference of 2 squares. Is y to the 4th a perfect square? Well, y squared times y squared equals y to the 4th. So it's a perfect square. The square root of it is y squared. Think of it this way. What's the square root of y to the 4th? Remember, we divide that. So it is a perfect square. It divides evenly by 2. So when I factor this, I'll keep my y, and I'm going to list both perfect squares. I would have y squared plus 12, y squared minus 12. So as I solve this, I have y equals 0. There's one answer. Not a double root or triple root there, just single 0. And then y squared plus 12 equals 0, and y squared minus 12 equals 0. Here's where it's kind of fun to see what's happening. I'm going to solve these for y. So I minus 12 from both sides, and I get y squared equals a negative 12. To get y by itself, I would square root both sides, and so hopefully here you're seeing I'd have y equals plus or minus, and when I square root a negative, I'm going to get an imaginary solution. So if you remember 12, hopefully you can break that down in your head now, because you've done a lot of it. Square root of 12 is always 2 root 3. So it's plus or minus 2 root 3. So here's actually 2 answers, because it's written as plus or minus. Over here, when I add 12 to both sides, I would have y squared equals 12. Square root both, and instead of it being imaginary, it's just a positive or negative 2 root 3. So this is going to cross the x-axis at 0. Oh, I forgot my I here. Sorry, guys. Let's do that better. How about that should be 2I root 3. Let me write that a little better for you. Y equals plus or minus 2I root 3. Does that look better? So I have my 5 times that it crosses the x-axis. Only 3 of them are real solutions. My real ones that I'm going to actually see on a graph are here, at the decimal for the square root of 12, positive and negative, at 0, and I'm not going to see this one. So what's this going to look like on my graph? How would I know maybe it's imaginary? Let's take a look. Here's my decimal for the square root of 12, and here's my 0. And it almost looks like they're straight lines, right? Because I had to zoom in so far to see this. Actually, how about I go on the axis? Holy cow. There's my 0 on the x-axis. So there's where my graph crosses the x-axis. If you can put this on your calculator and look at the actual picture, because I had to zoom in so far to show you the zeros, you might kind of see something interesting where the imaginaries would be, or maybe something to tell you it's imaginary. Remember, with a parabola, it's when the vertex didn't cross the x-axis or any part of it. You might kind of see something like that when you graph this. So that's, if you're interested in that, I think you should graph it on your graphing calculator. Our last couple here that we're going to do then is I'm going to, of course for this one, get my equation equal to 0 because I can't factor until I do that. So x to the 4th minus 13x squared plus 36 equals 0. This one I'm thinking is a little weird because I can't take out a GCF. So when I go to factor this, this is one of the examples of where we're using quadratic techniques on a problem that's not quadratic. This problem is a 4th degree, so quartic. And so I'm going to try to use my quadratic properties to factor. So I'm going to list my two parentheses. And I'm actually going to look at the factors of x to the 4th. It'd be x squared and x squared. So now when I'm finding factors of 36 when added together make negative 13, you could think about that and you'd get negative 9 and negative 4. So I just want to show you that if I actually FOIL this out, x squared times x squared minus 4 times x squared minus 9 times x squared plus 36. I do get that original problem. So it works to use the x squared here, just in case you were wondering if that was going to work. So from here now, I set each factor equal to 0 and solve. I'm going to add 9 to both sides, and when I square root, I get x to be plus or minus 3, so there's 2 of my solutions. Add 4 to both sides, and when I square root, I get x to be plus or minus 2. So there are my 4 solutions. They happen to all be real roots, so they cross the x-axis. They could sometimes be imaginary here, right? Especially when we're square rooting. Well, because we're square rooting. And if you look down at my graph, here's my negative 4, negative 3, negative 2, and my 2 and 3. So that's where my graph crosses the x-axis. Last one we're going to do together for this video. Same idea. So I want you guys to try this one and then hit unpause and see if you get the same answer as me. So I do not have a greatest common factor. I'm going to list my two factors as x to the 4th as x squared and x squared. Factors of negative 12 when added together make 1. That'd be a positive 4 and a negative 3. So when I set each factor equal to 0 and then solve, I'd minus 4 from both sides and then take the square root. Don't forget your plus or minuses. Square root of negative 4 is 2i. So I have plus or minus 2i. There's 2 solutions. Add 3 to both sides here. Square root of 3 is not a square root that breaks down, so it's okay for me to leave it just as plus or minus the square root of 3. There's my 4 answers. My calculator, of course, actually does the decimal values, so you'll see that I have the square root of 3 graphed right here. Those are my 2 real roots. My other 2 roots happen to be imaginary, right? So my 2 imaginary roots are plus or minus 2i. So those are the ones that you wouldn't see on the graph. If you have any questions on this, feel free to come talk to me about it tomorrow.